Okay, so let's go over a few examples of how we use specific heat capacity to calculate heat. Okay, so here goes the first one. We want to find out how much heat is absorbed when 50 mLs of water get warmed up from 22 degrees Celsius to 50 degrees Celsius. And we're being told that the specific heat capacity of water, liquid water, is 4.184 joules per grams degree Celsius. That's not a coincidence. That's in fact um, it's a direct corollary of the fact that the energy in SI units comes from measurements of water. But okay, we're going to find out the amount of heat. And here, all we're doing is look at the one substance, and we're increasing its temperature from 22 to 50 degrees Celsius. And so what we need to do is multiply the mass of the substance by the specific heat of the substance and the change in temperature. So T final minus T initial. All right, notice though that what we have been provided is the volume of water and not the mass. That's okay. If you are not being told anything in regards to density and the substance is water, you can assume that the density of water is 1 gram per ml, which automatically will make the 50 mLs equal to 50 grams of water. Okay, so that's if and only if I don't give you density in a problem. So we're going to input all the values. So we have 50 grams of water as a result of the density being 1 gram per ml. Heat capacity is 4.184 joules gram degrees Celsius. The final temperature is 50 degrees and the initial temperature is 22 degrees. So the first thing to do is to cancel out some units. The grams will cancel out and the degrees Celsius will cancel out. And all you will have left over is joules, units of heat. Okay, so 50 minus 22 is equal to 38 degrees Celsius. Oh, excuse me, 28 degrees Celsius. Multiplying that by the heat capacity and the 50 grams yields a value of roughly 5,857.6 joules, which if you divide by 1,000, you can obtain the same heat in terms of kilojoules. And this time, I'm rounding it up to the third significant figure since we only have 3 sig figs in the various numbers given. And I'm assuming that the temperatures are exact numbers for simplicity's sake. In future problems, you'll be given temperature values for which you'll actually have significant figures like 22.0 or 22.00, so do pay attention to those. Alright, so one last thing to mention before I move on to the next example. Notice that the temperature of the water increased from 22 to 50 degrees Celsius and the amount of heat is positive 5.86 kilojoules of energy. Alright, so I'm pointing that out because in the next example, we're going to be doing the opposite. We're going to start with 35 mLs of water and want to cool down the water from 83 degrees Celsius down to 37. And since this is water, we're still dealing with 4.184 joules gram degrees Celsius as the heat capacity. So we're going to calculate the amount of heat released. All right, so notice that change. We're not absorbing heat anymore because we're not increasing temperature. We're now releasing heat as a result of decreasing the temperature. But we still use the same equation, Q equals mcat. Alright, so the mass, once again, because this is water and density is not being mentioned, we assume it to be 1 gram per ml, at least the density. So we can use that to change the 35 mLs to 35 grams. The heat capacity is still 4.184. And the final temperature is 37, the initial is 83. Now what's going to happen is that when you carry the subtraction for the temperatures, you will end up with a negative change in temperature. And that negative change in temperature multiplied by 4.184 multiplied by 35 will cancel out the grams and the degrees Celsius, but more importantly will give you an answer that will be negative. Alright, so in this case, negative 6,736.2 joules. And if you divide by 1,000, this will give you the answer in kilojoules, which rounded up to 3 sig figs ends up being negative 6.74 kilojoules. And so this is the big point I was trying to make. If you decrease the temperature in a problem, you will end up with negative heat, meaning that you release or got rid of energy. On the other hand, if you do increase the temperature, the amount of heat that you'll end up with will be positive because you have absorbed that extra heat within your system. All right, so here, upon cooling down the substance, heat is lost. That's, big takeaway from this problem. All right, so in the next video, I'm gonna give you the definition of the zero law of thermodynamics, and we'll do a number of examples. So let's stop the video right here, and let's move on to the zeroth law.